Okay. It says show that the expected value for a female liking pop is 19. Sorry, typo on mine. So we're going to go through and find the expected value. Remember, the expected value is not needed in order to run this test. So you don't actually need to find any of the expected values in order to run this test. But it is a classic question to ask in a test for independence because it's actually a probability question in disguise. So the formula that we have up there, the expected frequencies are C over N when we're talking about row total, column total, and total total. It's actually just a shortcut from the calculations you've been doing from your previous unit. So if we were talking about the expected number of something to have happen, we normally find the expected value by finding the probability of something happening and then multiplying it by the total. If it has a probability of occurring 0.13 times and you have 100 people, how many people would we expect to have it happen? 13, right? You take that 0.13 and multiply it by 100. Out of 100, we would expect 13. So the same thing goes for any type of expected value, except for when we're talking about probability distributions, we have to use our summation formula. But for the most part, anytime we're talking about an expected value, we take the probability of that opportunity and then multiply it by the total amount that we have. So the total amount that we have is 80, and it says it up top at the very beginning of the problem. The probability that we're looking for is a female and they like pop. So it's an intersection, right? That they're female and they like pop. So if we were to break that down, it would be the probability that they are female, the probability that they like pop, and multiply those probabilities together, and then you multiply the 80. So I've broken down that intersection into a multiplication of the two separate things. Now remember, I can only do that if my two variables are what? So remember from unit 7, our probability unit, that we can only break up an intersection into multiplication only if the variables are independent. So when we're breaking down expected value, we're treating our variables like they are independent because it's what we expect to have happen, right? If our null hypothesis is that they are independent, then we expect for them to behave like they're independent. So we're comparing, okay, probabilities if they are independent, giving us a expected value, and then looking at our observed values, and we're saying, hey, is the difference between these statistically significant enough for us to say that they are or are not independent? So it's kind of a continuation of what we learned in Unit 7 with regards to what it means to be independent, which is kind of cool. So probability of just being a female, you have to look at the total number of females, 38, and you have to put it over the total. The probability of being a female is 38 out of 80. Okay, so then the probability of liking pop, that's a total of 40 people who like pop, so 40 out of 80. And then I would multiply it by our total number of people because we're looking for expected value. I'm going to put it as 80 over 1. Now, remember that our expected values are always row total times column total divided by total total. Total total is 80, right? Row total is 40. Is 38. Column total is 40. Notice if I simplify this multiplication, I can cancel out one of these 80s with an 80 down below because they're all being multiplied up top and they're all being multiplied down below. And since fractions are just division, they undo multiplications. So if I have an 80 up top and an 80 down below, I can just cancel them out. Notice that what I'm left is the row total times the column total divided by the total total. That's where the formula comes from, is it's just breaking down what it means to find an expected value, probability multiplied by the total, breaking it down as if the probability was independent, because that's what we expect to have happen. And then things simplify out that we can do this shortcut here. I don't recommend memorizing this formula because I don't recommend memorizing anything in this class because over 2 years, if you memorize all of the shortcuts, it's just too many things to have memorized. Instead, realize that this is a probability question in disguise, that you just need to find the probability of this occurring, treating it like it's independent, and then you can like remember, oh, that's right, there's a shortcut that goes with it, and you can then just do 38 times 40 divided by 80 and be able to solve it all out. This tends to be one of the more complicated things that students struggle on, which is why I'm spending a lot of time with this question. So hopefully I didn't over-explain it and I explained it just enough. Once you multiply it out, it becomes 19. So we have now shown that this is what happens. Okay, expected values, last up. Now it says write down the number of degrees of freedom. Since I've already shown you how to do it above previously, using this problem as an example, I'll have you go ahead and do it on your own. Remember that the degrees of freedom is equal to the number of options on the rows minus 1 multiplied by the number of options on the columns minus 1. Rows, there are 3. Columns, there are 4. Remember, we don't include the totals as an option. So it's just 1, 2, 3, 4, and then 1, 2, 3. So that's 2 times 3, which is 6. Did we have to write that all down? No, because it just said write down, which means it's just write it down, right? So you could have just written down 6, but I wanted to show you the process. Okay, now we're going to actually run the test. So now's where we're going to look at our calculator steps. So hopefully you wrote them down above earlier, and let's go ahead and start practicing it. So our chi-squared goodness of fit test needs to start with making a matrix. So menu, matrix, which is 7, create matrix. Number of rows. There are 3 rows. This is one of those things that if you press down automatically, it goes down to 2. So just be aware of that you have to press right 2 times and then press down. It's annoying, but it's just what's going on. There's 4 columns. Again, we do not include the totals in this. We just put in the observed frequencies. And now it's made a blank matrix for you that has the same dimensions as what we've seen above, minus the totals. And so then we just go ahead and put those numbers in. 16, scroll over, 9, scroll over, 2, scroll over, 6. Next. Once you have filled in all of those numbers for the matrix, you then need to store the matrix. It means you just need to really just give a name to this matrix. So what I've done is I've scrolled to the right, where you notice the blinking cursor is now to the right of the matrix. I can't scroll to the right anymore. I hit Control and then vars, which is just above 9 right here. And it's done this little arrow. It's because I'm going to store it. And here's where I put my title. I could just call it A and then press enter, and it's like, okay, cool. I always title it OBS, short for observed, just because it helps me keep clear what's going on in my brain. When you click enter, it just shows you the same matrix. It's just saying, done, we've stored it. This is now considered the observed matrix, whatever you titled it as. So now I've created my matrix, I've stored my matrix. I now need to run the test, and I can reference my matrix in the running of the test. So I go back to menu, I go to statistics, I go to stat tests, and I'm doing my chi-squared two-way test. It's 6, 7, 8, which is nice. Observed matrix. This is where you put in your title that you gave that matrix. Since I titled it OBS, I just type in OBS. I'm literally just using the keypad down below, OBS. If you titled it A, you just have to put A. But this is why you have to name or label your matrix so you can reference it for this test. So then you run it, and it gives you this breakdown. Notice the title, it's a chi-squared two-way test. The chi-squared value's here, the p-value's here, and it even gives you the degrees of freedom. So just realize you don't have to calculate the degrees of freedom. It doesn't ask you for the degrees of freedom, and your calculator will just give it back to you. So that's something that you could just use your calculator for in future chi-squared for independence tests. Whereas for goodness of fit, you do have to calculate it beforehand. Okay, so it said to find that chi-squared value. So that chi-squared value is 10.8 for 3 sig figs. And then our p-value is 0.0964 for 3 sig figs. Remember that second zero also does not count as a sig fig because it hasn't been bounded yet by another integer. Okay. And from here on out, it's the same as our other hypothesis, right? If P is low, reject the H sub O. If P is high, we fail to deny. And remember that the chi-squared is then flipped around from that. You can use any of that because we've been given a critical value, which gets compared to the chi-squared. Critical value was 11.345. We've also been given a significance level, which is compared to the p-value. You can use either or of those two options in order to draw a conclusion for this test. So go ahead and draw a conclusion for this test. I'm going to use the p-value, and the p-value is 0.0964, and our significance level is 1%. Now, if you have a hard time comparing numbers that look like that, remember that if you just match the number of decimal places, it's a little bit easier to see. How you match the number of decimal places is adding zeros onto the decimal number that doesn't have enough decimal places. This has 4 decimal places, so I'm going to add in 2 zeros to make it also have 4 decimal places. 100 compared to 964, 964 is larger. Okay, so my P is high, so we fail to deny.